We've all been there, glued to the screen as a building collapses in a cloud of dust and debris. Or maybe it's the brilliant burst of a firework that captivates us, the night sky awash in vibrant colours. Explosions, in all their destructive and beautiful glory, have a way of captivating the human imagination. It's a strange fascination, some might say, to be drawn to such raw power. But there's no denying the thrilling spectacle of an explosion, a fleeting moment where energy transforms matter right before our eyes. Perhaps it's the sheer force, the raw energy unleashed in an instant that draws us in. Maybe it's the visual spectacle, the mesmerizing dance of fire, light and sound. Or maybe, just maybe, it's the inherent danger, the reminder of the awesome and sometimes terrifying forces at play in our universe. Whatever the reason, explosions occupy a unique space in our collective consciousness, simultaneously awe-inspiring and fearsome. From the smallest firecracker to the most powerful supernova, explosions are a fundamental part of our universe. They're the grand finales of stars, the birth cries of new galaxies, and the explosive force behind volcanic eruptions that reshape our planet. But explosions aren't just confined to the vastness of space or the depths of the Earth. They're woven into the fabric of our history and our daily lives. Explosions are more than just visually stunning events. They're intricate scientific processes governed by the laws of physics and chemistry. At their core, explosions are rapid expansions of volume, often accompanied by the release of a significant amount of energy in the form of heat, light, and sound. This rapid expansion creates a pressure wave that can be incredibly destructive, shattering objects, leveling structures, and even altering landscapes. But what triggers such a violent release of energy? The answer lies in the heart of matter itself. Explosions can be broadly categorized into two main types: chemical explosions and nuclear explosions. Chemical explosions, as the name suggests, involve rapid chemical reactions that produce a large volume of gas in a very short time frame. These reactions are often exothermic, meaning they release heat, further fueling the expansion and creating the characteristic fiery inferno we associate with explosions. Nuclear explosions, on the other hand, operate on a whole different level of energy. Instead of rearranging atoms through chemical bonds, nuclear explosions involve the nucleus of an atom itself. Through processes like fission, where an atom's nucleus is split, or fusion, where atomic nuclei combine, unimaginable amounts of energy are released. This energy, far exceeding anything achievable through chemical means, is what gives nuclear weapons their devastating power. The spectrum of explosions is as diverse as it is fascinating. At one end, we have the controlled bursts of pyrotechnics, carefully orchestrated to paint the night sky with vibrant colours. These miniature explosions, while visually impressive, pale in comparison to the awe-inspiring power of volcanic eruptions, where molten rock, ash and gases are ejected from the Earth's interior in a spectacular display of our planet's raw power. Then, there are the accidental explosions, often the result of human error or unforeseen circumstances. Industrial accidents, such as the devastating explosion at the port of Beirut in 2020, serve as stark reminders of the potential dangers of mishandled explosives. These events, while tragic, highlight the importance of understanding the science of explosions and implementing stringent safety protocols. But perhaps the most awe-inspiring explosions are those that occur in the vast expanse of space. Supernovae, the cataclysmic deaths of massive stars, release more energy in a few seconds than our sun will emit in its entire lifetime. These cosmic explosions, visible across unimaginable distances, are a testament to the immense forces at play in our universe and serve as a poignant reminder of the transient nature of even the most massive celestial objects. Let's delve into the heart of a chemical explosion. Molecules are in constant motion, vibrating and colliding. Add the right ingredients, and these collisions can escalate into an explosion. A chemical explosion is a runaway chain reaction. This rapid release of energy creates the pressure wave, heat, light, and sound. Section 2. Fueling the fire. The ingredients of a chemical explosion. So, what are these explosive ingredients? These molecular troublemakers that can unleash such destructive power? Well, they're not as exotic as you might think. In fact, many everyday substances have the potential to become explosive under the right conditions. It all comes down to the right combination of fuel, oxygen and heat, often referred to as the fire triangle. Let's take a look at each element. Fuel, as the name suggests, provides the raw material for the explosion. This could be anything from flammable liquids like gasoline and ether to combustible solids like wood, paper and even certain types of dust. These materials contain chemical bonds that, when broken, release energy. Next, we have the oxidizer, the ingredient that allows the fuel to burn rapidly. Oxygen, the most common oxidizer, is all around us in the air we breathe. Other substances like chlorine and fluorine can also act as oxidizers, supporting combustion even in the absence of oxygen. Finally, we need a spark, a source of ignition to set the whole process in motion. This could be a flame, a spark from an electrical short circuit, a sudden impact, or even the intense heat generated by friction. The ignition source provides the initial energy needed to break the chemical bonds in the fuel, releasing heat and triggering the chain reaction that leads to the explosion. Section 3. Nuclear reactions, the heart of unfathomable power. Now let's shift gears and venture into the realm of nuclear explosions, a domain of power that dwarfs even the most potent chemical explosions. While chemical explosions involve the rearrangement of atoms through the breaking and forming of chemical bonds, nuclear explosions tap into the very heart of matter itself, the atom's nucleus. Imagine the atom as a bustling city, with the nucleus as its central power plant. The nucleus, home to protons and neutrons, holds the vast majority of the atom's mass and is bound together by an incredibly strong force, aptly named the strong nuclear force. To unleash the energy within the nucleus, we need to tamper with this force, and that's where nuclear reactions come into play. There are two primary types of nuclear reactions that can lead to explosions: fission and fusion. Fission, the process that powers atomic bombs, involves splitting a heavy atom's nucleus, like uranium or plutonium, into lighter elements. This splitting releases an enormous amount of energy, along with neutrons that can trigger further fission reactions in a self-sustaining chain reaction. Fusion, on the other hand, involves combining the nuclei of light atoms, like hydrogen isotopes deuterium and tritium, to form heavier elements like helium. This process, the same one that powers the Sun and other stars, releases even more energy than fission and is the basis for thermonuclear weapons, also known as hydrogen bombs. Section 4. Fission versus fusion, a tale of two atomic processes. To understand the stark contrast between fission and fusion, imagine a game of atomic billiards. In fission, we're using a cue ball, a neutron, to break apart a racked set of heavy billiard balls, uranium or plutonium nuclei. The impact sends the balls scattering, releasing energy in the process. Fusion, however, is more like merging two soap bubbles. Imagine bringing two bubbles together gently. At first, they resist merging, but with a little more pressure, they suddenly coalesce into a single, larger bubble, releasing a burst of soapy air. In fusion, the pressure comes from extreme temperatures and densities that force the positively charged nuclei of light atoms to overcome their electrostatic repulsion and fuse together. The key difference lies in the energy requirements and the byproducts. Fission reactions are relatively easy to initiate. All it takes is bombarding a fissile material like uranium-235 with neutrons. However, fission produces radioactive byproducts like cesium-137 and iodine-131, which pose significant long-term health and environmental hazards. Fusion, on the other hand, requires extreme temperatures and pressures like those found in the core of the Sun. Achieving these conditions on Earth is a technological challenge, but the rewards are enticing. Fusion reactions release even more energy than fission and produce far fewer radioactive byproducts, making it a potentially cleaner and more sustainable energy source in the future. Section 5. The shadow of power, the lasting impact of nuclear explosions. The sheer power of nuclear explosions has left an indelible mark on human history, for better or for worse. The atomic bombings of Hiroshima and Nagasaki in 1945, while marking the end of World War II, ushered in the nuclear age and the chilling reality of humanity's capacity for self-destruction. The mushroom clouds that rose over those Japanese cities serve as a stark reminder of the devastating consequences of nuclear weapons. The immediate devastation, the lingering radiation sickness, and the long-term health effects on survivors and their descendants stand as a grim testament to the horrific power we unleashed. Beyond the immediate human cost, nuclear explosions have also left their mark on the environment. Radioactive fallout from nuclear tests conducted during the Cold War continues to contaminate soil, water, and air in certain parts of the world, posing long-term health risks. The legacy of nuclear weapons is a complex and sobering one. On the one hand, they represent a technological marvel, a testament to human ingenuity and our ability to unlock the secrets of the atom. On the other hand, they serve as a stark reminder of the immense responsibility that comes with such power and the urgent need for international cooperation and disarmament to prevent a nuclear catastrophe that could threaten the very future of our species. The day the sky exploded, June 30th, 1908, Tunguska, Siberia. Picture this, the sun rising over the dense forests of Tunguska. Suddenly the sky erupts in a blinding flash, followed by a deafening roar. What caused this event? The Tunguska event flattened over 80 million trees across 830 square miles. Witnesses described a fireball and a powerful shockwave. Theories range from a meteoroid to an alien spacecraft. The Tunguska event remains a stark reminder of cosmic power. Section 2. Trinity. Birthing a new era of power and fear. Our next stop takes us to the desolate plains of New Mexico, to the pre-dawn hours of July 16, 1945. Deep in the New Mexico desert, a team of scientists and engineers gathered for a top-secret test, codenamed Trinity. Then, at 5:29 a.m., the world changed forever. A mushroom cloud, ominous and awe-inspiring, rose tens of thousands of feet into the sky. Just 3 weeks after the Trinity test, the world witnessed the devastating power of nuclear weapons firsthand in Hiroshima and Nagasaki, Japan. The bombings of Hiroshima and Nagasaki remain the only use of nuclear weapons in warfare, shocking the world and searing the horrors of nuclear war into the collective human consciousness. The images of the mushroom clouds, the charred ruins, and the suffering of the hibakusha serve as a constant reminder of the human cost of nuclear weapons. On April 26, 1986, Pripyat in the Soviet Union became synonymous with one of the worst nuclear disasters in history, Chernobyl. A catastrophic power surge led to explosions and a fire at reactor number 4, spewing radioactive material into the atmosphere. The disaster highlighted the potential dangers of nuclear power and the importance of safety protocols and international cooperation. Volcanic eruptions, those fiery spectacles of Earth's raw power, have shaped the very land masses we inhabit. The eruption of Mount Tambora in 1815, the most powerful in recorded history, plunged the Northern Hemisphere into a volcanic winter. The Tambora eruption serves as a stark reminder of the interconnectedness of Earth's systems and the far-reaching consequences of even seemingly isolated events. Controlled demolition offers a precise and efficient solution for removing towering structures. Experts meticulously plan these implosions, strategically placing explosives and calculating the precise timing needed for a safe collapse. When executed correctly, they demonstrate how even the most destructive forces can be harnessed for specific purposes, transforming urban landscapes with surgical precision. In mining, explosions play a vital role in accessing resources hidden within the Earth's crust. Explosives are used to break up rock mass, creating tunnels and open pits that allow access to valuable resources. The actual blast is a carefully orchestrated event, balancing resource extraction and minimizing environmental impact. Explosions, in the form of controlled rocket propulsion, are the driving force behind our ventures into space. At the heart of a rocket lies the combustion chamber, where fuel and oxidizer combine in a controlled explosion, generating immense thrust. Liquid-fueled rockets offer high thrust and precise control, while solid-fueled rockets provide simplicity and reliability. Explosions add excitement and realism to entertainment, particularly in special effects. Special effects artists use practical effects and CGI to create realistic and visually stunning explosions, whether it's a heart-stopping action sequence or a breathtaking visual spectacle. Explosions in the hands of skilled artists have the power to transport us to other worlds. The future of explosion control lies in advancements in technology, materials science, and our understanding of these powerful events. Researchers are developing safer and more environmentally friendly explosives and smart explosives that can adjust their detonation properties in real time. Advancements in sensor technology and predictive modeling enable better understanding and anticipation of explosions. Taming the beast of explosions requires technological innovation, rigorous safety protocols, and a deep understanding of the forces we're dealing with. Ensuring safety in a world where explosives are essential tools is paramount. Explosion safety begins with meticulous planning, rigorous safety protocols, and a culture of vigilance. Education and training are the cornerstones of explosion prevention, with workers needing a deep understanding of the materials and risks involved. Creating a culture of safety within organizations and industries that handle explosives is crucial. Early detection of explosive threats is crucial for mitigating potential damage and saving lives. Technologies like trace detectors and K9 units are used to identify explosive materials. The future of explosive detection lies in developing more sensitive, faster, and versatile sensors. Blast mitigation involves designing structures and materials that can withstand or deflect the forces of an explosion. Reinforced concrete and blast-resistant windows are key elements in protecting lives and infrastructure. These materials are designed to absorb energy, preventing shattering and reducing the risk of flying debris. Understanding the enemy, the science of blast mitigation. Designing effective blast mitigation measures requires a deep understanding of the physics and dynamics of explosions. When an explosive detonates, it generates a rapidly expanding sphere of hot, high-pressure gas. This expansion creates a shockwave, a wall of compressed air that travels outward at supersonic speeds, followed by a blast wind, a powerful rush of air that can last for several seconds. The shockwave is the most destructive element of an explosion, capable of shattering concrete, collapsing buildings, and causing severe injuries. Its intensity diminishes with distance, but even at considerable ranges it can still pose a significant threat. Blast mitigation strategies aim to disrupt the shockwave's path, reduce its intensity, or deflect it away from vulnerable targets. This can involve creating physical barriers like earthen berms or reinforced walls, or using specialized materials that can absorb and dissipate the shockwave's energy. Another approach involves designing structures to withstand the blast loads. This can involve strengthening existing structures or designing new ones with blast resistance in mind. Techniques like base isolation, which decouples the building from the ground, and energy-absorbing facades can help minimize the impact of blast waves. Section 5. A Safer Tomorrow, the Quest for Explosion-Resistant Materials. The quest for safer explosives and more effective blast mitigation strategies is an ongoing endeavor, driven by advancements in materials, science, engineering, and our understanding of the complex dynamics of explosions. Researchers are exploring a range of innovative approaches, from novel explosive formulations to bio-inspired materials that mimic nature's protective mechanisms. One promising area of research is the development of nano-engineered materials with enhanced blast resistance. These materials, with their unique microstructures, can exhibit exceptional strength, toughness, and energy absorption capabilities, making them ideal candidates for blast-resistant structures and protective gear. Another area of exploration is the development of self-healing materials that can repair damage caused by explosions, much like living organisms can heal wounds. These materials, embedded with microcapsules containing healing agents, can automatically repair cracks and fissures, restoring structural integrity and preventing further damage. The future of explosion control may also lie in harnessing the power of nature itself. Researchers are studying the blast-resistant properties of biological materials like spider silk and abalone shells, which exhibit remarkable strength and toughness despite their lightweight nature. By understanding the underlying principles that govern their resilience, we may unlock new avenues for designing lighter, stronger, and more sustainable blast-resistant materials. Section 1, the two sides of the coin, destruction and creation. As we've journeyed through the fiery heart of explosions, we've encountered a duality, their capacity for immense destruction and their surprising role in creation and progress. It's a paradoxical relationship, a testament to the power of energy in its rawest forms to both obliterate and build. We've witnessed the destructive force of explosions firsthand, from the chilling historical accounts of Hiroshima and Nagasaki to the sobering reminders of industrial accidents like the Port of Beirut explosion. These events serve as stark warnings, etched in the collective memory of humanity, of the devastating consequences that can arise from unchecked power or a lack of respect for the forces we wield. Yet, amid the wreckage and the cautionary tales, we've also discovered a more nuanced narrative, a story of how humans have harnessed the power of explosions for good. Controlled demolition, for example, has transformed the process of dismantling outdated structures, making way for urban renewal and progress. Mining, though not without its environmental challenges, relies on explosives to extract the raw materials that fuel our modern world, from the smartphones in our pockets to the energy that powers our homes. Even space exploration, that grandest of human endeavours, hinges on the controlled explosions that propel rockets skyward, pushing the boundaries of human ingenuity and our understanding of the cosmos. Explosions, it seems, are an undeniable part of our story, a force that has shaped our past, shapes our present, and will undoubtedly continue to shape our future. Section 2. Respecting the force. A responsible approach to explosions. The key to navigating this volatile landscape lies in respect. Respect for the immense power of explosions, for the intricate science that governs their behaviour, and for the very real consequences, both intended and unintended, that they can unleash. This respect must permeate every aspect of our interaction with explosives, from their development and handling to their application and disposal. The quest for safer explosives, for instance, is not merely a scientific challenge, it's a moral imperative. Minimizing the environmental impact of explosions, reducing their toxicity, and developing alternatives that pose fewer risks to human health are not optional objectives. They are essential steps in our journey toward a more sustainable and responsible use of these powerful forces. Similarly, the development and implementation of robust safety protocols, early warning systems, and blast mitigation measures are not bureaucratic hurdles to be overcome, but rather essential safeguards that protect lives, infrastructure, and our shared environment. The human cost of explosions, as history has tragically shown, is far too high a price to pay for complacency or negligence. Respect for the force also means engaging in open and honest dialogue about the ethical implications of our explosive endeavours. The development of new and increasingly powerful weapons, for instance, demands careful consideration of their potential consequences and the establishment of international agreements and safeguards to prevent their misuse. Section 3. The explosive future, innovation and safety in a volatile world. Explosions will continue to play a pivotal role in our world. The quest for new energy sources and space exploration relies on harnessing these powerful forces. Innovation and safety intersect in the future of explosions. Nanotechnology offers blast-resistant materials with unprecedented strength. Imagine buildings and gear that can withstand explosions, protecting lives. Smart explosives offer precision and control in demolition and mining. Embrace innovation, prioritize safety, and wield explosive power responsibly.